Hello, everyone. Okay, here's an introduction to fundamental aspects of mass spectrometry. Or a large screen, and we'll be underway. It's that easy. We've seen the infrared and a little bit of the UV vis, so now we'll take a look at the mass spec. When I was a graduate student at the University of Nebraska-Lincoln, Hamilton Hall, I think it's a 7 or 8-story building. The Midwest Center, the NSF-sponsored Midwest Center for Mass Spectrometry, was located in the basement. And I recall some of the early recognizable modern mass spec machines downstairs in the basement. And, I used to go down there a lot and interact with that research group. They were doing early work on the Love Canal, which is a classic in environmental contamination up in Niagara Falls area, outside of Buffalo. The old Hooker Chemical Company dumped a whole bunch of barrels, and they leached into the Niagara River and then into eventually Lake Ontario. It was a classic early application of mass spectrometry. They were doing soil analyses. Dr. Gross was the head of the Mass Spec Center when I was there at the time. Okay, it all begins with J.J. Thomson, the discoverer of the electron. This is not spectroscopy because it does not involve any electromagnetic radiation, absorption or emission. So we call it mass spectrometry. Those of you that are completing the course with Dr. Mulcahy, I'm sure you have a very, very good background now. And we do have people in the class that don't have any background in mass specs, so we must be patient and help everybody get up and running with very fundamental aspects in just one portion of this course. You have a sample, and let's say it's a gas. Let's say well, it's going to be a gas. Let's suppose you separated it by chromatography, HPLC or GC. We have an integrated GC mass spec. So you have this sample going through neutral molecules. It's going to get hit with an electron beam. So you're going to heat this up, maybe 60 electron volts. That's a unit of energy that we use in mass spec. And you're going to heat it up. You're going to have a positively charged repeller plate, a negatively charged accelerating and focusing plate. And when you heat the filament up, you get an electron beam. You're going to hit the compound with an external electron of high energy and knock an electron out somewhere in the molecule. It will either be, most likely, right, a weakly held lone pair electron or a pi bond electron. If there's none around, then it'll go for a sigma bond. But somewhere in the molecule, an electron is going to get knocked out. Neutral molecules, neutral fragments, and negative ions are evacuated in the fundamental approach by a high vacuum pump. The only thing getting through the machine, positively charged entities. It's a world of carbocations. And what you're going to do is smash the molecule to pieces. The initial cation, you lost an electron into pieces. Like a jigsaw puzzle, you work backwards. The positively charged materials go through the radius of curvature with a magnet, and they accelerate and separate on the basis of ionic mass. You'll have an analyzer tube, and it will detect positively charged ions. They will be deflected by ionic mass according to M over Z. That would be the ionic mass divided by Z. In normal operation, Z is equal to 1. It's an electron. Then you get an ion exit slit and a collector and then a recorder. The data is usually reported in the terms of a bar graph. The mass spec records only positively charged fragments. They be either cations or radical cations. It's a world of arrows, 1 and 2 pronged arrows. And M over Z is your mass to charge ratio of the fragment. Information obtained from a mass spec. The molecular ion M measured to the nearest whole number or up to 4 decimal places, high resolution mass spec in that case. This is where you precisely determine molecular weights of compounds. You can use freezing point depression, boiling point elevation, colligative properties, osmotic pressure, but mass spec in this day and age is the easiest way to generally determine a molecular weight of a substance. If you have a natural sample of carbon, you will see the carbon 12, 13, and 14 with the ratios comprising 12.011 for carbon on the periodic table chart. Isotopic peaks, M+1, M+2 can be detected when you have a deuterium or a C13. As the molecular weight increases, you have a greater chance of seeing deuterium, carbon-13, and you will start to see M+1, M+2 to a greater extent. Now, the biggest peak to the right, or line to the right in the spectrum, would be your molecular ion. Here it would be 72. See the little trace of 73? That's a carbon-13 or a deuterium. But there is your molecular ion. The starting material had a molar mass of 72 grams per mole. Do you always see the molecular ion? Usually, but not always. Alcohols are notorious for not exhibiting molecular ions, and you'll see why as we go along. That's your M, molecular ion. M+1 is seen as well. Typically, M and the isotopic peaks are the highest masses in the spectrum. Exception, a compound whose molecular ion completely fragments, like an alcohol. The high resolution mass of the molecular ion provides the molecular formula directly. High resolution mass. So you can get the molar mass 4 places to the right of the decimal point. Usually in a journal with a new compound, they want combustion analysis. They want the elemental analysis as carried out by combustion analysis. Empirical formula, molecular formula. In some cases, the compound is very fragile, and when you package it and send it out for elemental analysis, it has decomposed by the time it gets there. In some cases, then, the journal will allow publishing the high-resolution mass spec to show the compound is there. Now, the high-resolution mass of the molecular ion provides the molecular formula directly, and then the whole number mass of the molecular ion and the relative intensities of M1 and M2 can also provide the molecular formula. Fragment masses and intensities together provide structural information. We see in the bar graph the molecular ion at 72, and then we're detecting radicals or radical cations. We're detecting cations or radical cations. We'll get into this. And there you're seeing them at 43 and 57. Now, you usually get a molecular ion and a base peak. The base peak will be the peak that shows up most commonly. Sometimes the molecular ion is the base peak, but usually it's not. Molecular ion, M-15. So you're losing, in this case, a methyl radical. You don't detect the 15, but you're going from 72 minus 15 to 57. And that generally suggests you're losing a methyl radical and detecting a new cation at 57. Same with the M-29. To exhibit a 43 to 29 would be loss of an ethyl radical, C2H5. The base peak has the greatest intensity, as I said, in the spectrum. Intense peaks correspond to relatively stable cationic and or relatively stable radical species lost. Resonance, induction effects, all will be observed here.
You can get thermodynamic data here, which is very important in the physical chemistry. Mass spec is also employed by physical chemists as well as analytical chemists. The fragments lost also provide structural information indirectly. For example, the fragment M over Z, 57 over, I defined Z as 1, resulted from the loss of a methyl from the molecular ion. So you have a new cation at 57 because you're losing, in this case, a methyl radical. Given its intensity, M over Z 57 must be the secondary butyl carbocation, not the primary butyl carbocation from butane. Here's the mass spec of pentane, typical bar graph, molecular ion at 72. And on the preceding slide, I said butane, I meant pentane. There it is at 72. If you were to look in a library of compounds, I guess DBS, you would find that pentane exhibits this spectrum. And there you see the base peak at 29. So in other words, pentane is losing an ethyl. The initially formed pentane cation is losing an ethyl radical, and you're seeing the 43, which would be the N-propyl cation. There's your M minus 15, 57, loss of a methyl radical. You're even detecting a 15 cation. Do you see that? You're also detecting a 29 cation. So what's important is what you see, but also is important is what is the difference. What are you losing that's not being seen? The 57 peak is the primary butyl cation when you crack out 29. The base peak of 43 in the mass spec indicates the preference for C2 to C3 fragmentation. In other words, cracking a methyl off is not to be preferred to cracking off an ethyl radical. Now look very carefully at this diagram and don't proceed until it makes sense. Over on the left, you see in brackets a radical cation. You knocked an electron out with the filament. You're detecting this radical cation. There's an unpaired electron somewhere in the whole bunch of sigma bonds. You knocked a sigma electron out. So you have a positively charged material which is also has an unpaired electron. Do you remember the Birch reduction? Go back to your organic to chapter 9, triple bonds. Recall the Birch enables you to take group 1 metal and liquid ammonia and reduce down an alkyne to a transoid alkene. The Lindlar gave you cis, the Birch gave you trans. The intermediate for that mechanism, which was 4 steps, involved a radical anion. So here you're seeing a radical cation. Now we're detecting 43, that means the loss of an ethyl radical. We're detecting 29, loss of an N-propyl radical. You're detecting 57, you cracked out a methyl radical. You're detecting a methyl cation, that means you lost an N-butyl primary radical. All fragments originate from the molecular ion. The mass of the radical species lost in a fragmentation is the difference between the MZ values, M over Z values of the fragment ion and the molecular ion. Here's isopentane. So it's a constitutional isomer of N-pentane. We have branching, very important. Who developed mass spec? The oil industry. Who developed NMR? Big pharmaceuticals, big pharma. They developed mass spec, the oil industry, so they could determine hydrocarbon characteristics from crude oil and now natural gas. So if there's money to be made, they'll put money into developing, and that's what did this. The Petroleum Research Fund, big oil developed mass spec. It's used now, ironically, with environmental problems in litigation. This is mass spec of isopentane, as I said. 72, 57, 43. Is it identical to N-pentane? No. It will be different enough. There's a strong 57 peak because by cracking off a methyl branch, and that's generally what happens frequently, you generate a secondary butyl radical cation. Here's what's taking place. You have the molecular ion, a radical cation, chopping out a methyl radical, giving you, in this case then, if you lose the methyl radical, now you have a classic cation at 57. So the methyl carries away the unpaired electron, and that yields the detectable 57, which is a classic cation. The molecular ion is a radical cation. Really an amazing field of mass spec. It really is. Very strongly analytically oriented people can be found here. Here's a two-fragment loss from the molecular ion. 42 and 41. These ions arise from loss of the ethyl radical in either a hydrogen atom or diatomic hydrogen from the pentane molecular ion. So unusual patterns can occur. Once again, like infrared, analysts with mass spec will try to identify 25 different peaks. We're going to try to fish out 2, 3, maybe 4 or 5 at the most. We're going to get a molecular ion, a base peak, and we're going to look for some other pieces. So here you make, to get 42, the only way we can envision it is that you're losing an ethyl radical and a hydrogen atom. And that would give you then 42, which is a radical cation. That's what it is. Or you can lose an ethyl radical and diatomic hydrogen and get a resonance stabilized allyl cation. Entropy favors a lot of things being formed, right? This order. All fragments, however, originate from the molecular ion. Exception, tandem mass spectrometry, where fragments of fragments are observed. And I can't help you with tandem mass spec. I only know fundamental mass spec. Isotopes in mass spectrometry. The N+1 peak is a contribution from either a deuterium or a C13 being present. The N+2, that could be an O18, or from two heavy isotopes, a deuterium, a carbon-13, or one of each in the same molecule, but that's your N+2. This is important, environmental litigation. A large N+2 peak suggests a compound containing either chlorine or bromine. A chlorine of N+2 is 1/3 the intensity of the molecular ion. A bromine, if N+2 is the same intensity as M. It's based on isotopic abundance. You see, with chlorine, you have 35 and 37 isotopes. And it's about a 3-to-1 ratio of 35 to 37. Now with bromine, look at the periodic table. With bromine, you're at 79.9 is what they show for atomic bromine on the periodic table. That's because you have contributions from 79 and 81, and they're about 50-50 naturally occurring, about 50-50. So then their periodic table comes in at 79.9, because that, of course, the atomic mass shown in the chart is a contribution from the isotopes that are contributing. Carbon, for example, 12.011, because you have a little bit of C13, a little bit of 14 that boosts it up to 12.011. Fluorine, there is one isotope, F19. Fluorine does not have any other partners. It's 18.98, or what we call 19. Here's some fragmentation patterns of alkyl halides. Good old-fashioned 1-bromopropane. You see the twin peaks, 122, 124? dead giveaway you have bromine in the molecule. And that's why this is so important in environmental litigation with organohalides in soil and water. 122, 124, and you see for each one an N+1 due to a deuterium or carbon-13, as we mentioned. If you see Twin Peaks in a court of law and you have an illegal drug containing bromine, they're going to settle out of court because the DA is going to bring in a forensic chemist, and the forensic chemist is going to say this compound, a controlled substance, known to have a bromine, there it is. There's the mass spectrum of the sample that was confiscated. So that's why right away they settle out of court, because as soon as the judge sees that, it's over. 79 and 81. Here's chloro, 2-chloropropane. You see the ratio? It's about 2.5, 3 to 1. 78 to 80. That's your 35 and 37 for chlorine. You can get combinations of bromine and chlorine. There are charts that help you with that. It's like a fingerprint then. Then there's the decomposition, 63 and 65. What's good for the goose, good for the gander. So all the way through, you're going to see that. This is very, very important, a fundamental term used in mass spec. Here's where arrows come into play, both double-pronged and single-pronged arrows. Alpha cleavage results from the homolytic cleavage of a CC bond at the alpha carbon. Arrows, rearrangements, resonance, induction, thermodynamic information, everything comes into play with mass spec. If we could only use mass spec the first week of organic, first couple of weeks, to illustrate all of the fundamentals that now will come to life after you've been doing it in lecture and organic with pencil and paper week after week, month after month. Okay, 2-chloropropane. Alpha cleavage. Now make sure you know how they define alpha. The alpha carbon is the one designated, the one that's bound in this particular case to chlorine. That is called the alpha carbon. Just like the alpha male in a pack of dogs. That's how you remember the alpha here. So you're going to have a 78 and an 80 because of 35 and 37 chlorine, right? Then you get homolytic cleavage. Homolytic cleavage, alpha cleavage. And that means you're going to crack a methyl piece off of the alpha carbon. So with 35 and 37, each one's going to produce a methyl radical by homolytic alpha cleavage, and you get two methyl radicals being kicked out, one by the 35 and one by the 37. Alpha cleavage occurs because, interestingly enough, the carbon-chlorine and carbon-carbon bonds have similar strengths. The species that is formed is a relatively stable cation. There's your initial product of alpha cleavage. You see the single-pronged arrows? And you get a resonance-stabilized chlorinium ion, just like good old Chapter 8 in organic, cyclic chloronium ion. So you have resonance contributor 1 and 2. Alpha cleavage, and remember, we're in the gas phase. We're not in solution. So, you have solvent effects in the round bottom flask. Just remember, in mass spec, it's in the gas phase. So you might say, well, how come there's a carbocation there? I thought we have no carbocation. When you add diatomic chlorine to an alkene in Chapter 8, you're in solution. Here you're in the gas phase. Alpha cleavage is less likely to occur in alkyl bromides because carbon-carbon bond is stronger than carbon-bromine. Let's survey the fundamental functional groups. Now, let's start with ethers. Okay, here's sec-butyl isopropyl ether, an unsymmetrical dialiphatic. We're getting action at 116, that's your molecular ion. And then the base peak is 43. We have other peaks at 101, 87, 57, and 41. Here's, now they jump from an ether to an alcohol. Here's 2-hexanol. Okay, it's a secondary alcohol. You're going to lose an electron, and that electron is going to probably get knocked out of a lone pair. In this case, see the oxygen losing a lone pair electron, or a pi bond. So here you're losing it from an oxygen lone pair. You define your alpha carbon, the one bound to the OH, and then you could have two alpha cleavages, one side or the other. One would yield at 87 a methyl radical, and the top one would yield a primary N-butyl radical and loss of a resonance stabilized 45. Those are homolytic alpha cleavages on both sides of the alpha carbon. Sometimes you'll have three sides. Depends on the structure. Now, a CO bond is cleaved heterolytically, with the electrons going to the more electronegative atom. So let's look very carefully at this. And here we have alpha cleavage. So remember, here's your prior slide, 102. So it's not going to be homolytic cleavage here. It's going to be heterolytic because of electronegative oxygen. Oxygen has a positive charge. It's under pressure. It's electronegative. So here we're going to do alpha cleavages, of course, as I showed you, yielding a detectable 45 and 87. And with pencil and paper, you see that what you're doing is moving a methyl radical out, alpha cleavage. And on the top one, it's loss of an N-butyl radical. That more electronegative atom, oxygen, is going to be satisfied. Now, a CC bond is cleaved homolytically in an alpha position because it can lead to a relatively stable cation. You make sure you go over the last slide and this slide very carefully with pencil and paper so you know the differences between heterolytic and homolytic cleavages. Okay, here you can have three alpha cleavages. First, you're going to crack out an ethyl radical. In the second case, lose a methyl radical. And in the other case, you're going to lose a different methyl radical. You're going to get peaks at 87, 101, and 101. Two sources of 101. Fragmentation patterns of alcohols. Barely see with this 1, 2, 3, 4, 5, 6, 2-hexanol. You get a barely detectable 102. Alcohols usually will form molecular ions that lose water almost spontaneously. Molecular ions from alcohols usually are not observed. Like alkyl halides and ethers, alcohols undergo alpha cleavage. You're going to lose an unpaired electron to get your molecular ion at 102. And then, like the halides and ethers, alpha cleavage on one side or the other, 45 and 87. In alcohols, you see, sometimes you don't get a molecular ion at all because the molecular ion is going to lose water. It's going to actually kick out a gamma hydrogen to form water. Entropy drives this and get a detectable 84. So now you have a gamma carbon getting into play. Excuse me. I've been spraying so much Lysol. As I'm recording this lecture, I'm free of that coronavirus, so time will tell what happens. At any one of these points, this could be my last lecture. Remember, I'm going to be 67 in June. Common fragmentation behavior in alkyl halides, ethers, and alcohols. 1, a bond between carbon and a more electronegative atom breaks heterolytically. A bond between carbon and an atom of similar electronegativity breaks homolytically. And the bonds most likely to break are the weakest bonds and those that lead to formation of the most stable cation. Here's a ketone. They give intense molecular ions, knock out a lone pair electron on an oxygen, detect a molecular ion at 86, alpha to form a resonance stabilized acylium ion at 43. Remember your Friedel-Crafts alkylation? It yields acylium ions. And you can also get the 71 acylium ion with loss of a methyl radical. Here's the Fred McLafferty rearrangement. Interestingly enough, Fred McLafferty was at the University of Nebraska-Lincoln, where I went years before me. Finished a master's degree, got into an argument with his PhD advisor, left the school. He later went to, when he got his PhD at another school, he went to Purdue University, where he became one of the founding fathers of mass spec. This reaction does not occur in a round bottom flask. It only is seen, this rearrangement, in the gas phase of mass spec. If you have flexibility in a molecule, you have single bonds here, so you can do rotational play, Newman projection stuff. It turns out that oxygen is greedy for an electron. And what it will do is grab hold of a hydrogen atom with an electron, and you will kick out ethene molecule. Entropy drives this. And you see you're involving in this rearrangement a gamma hydrogen. But you have to have rotational play, and it's usually a pseudo 5 or pseudo 6 transaction. This would be a 1, 2, 3, 4, 5, 6 atoms involved. It's usually 5 and 6. And that accounts for 58. Otherwise, you would say, where did it come from? How could that form? It's a rearrangement. That's it for the mass spec. You have enough. If you can get, look, benzene, I'm going to put a chart. I'm going to upload a chart to the learning module section. If you have a benzene in a compound, you're going to see a 77. If you have an aromatic ketone, that can crack off to give a resonance stabilized benzyllium ion at 105. Murph was doing his capstone with some aspect of ibuprofen. He was trying to do Friedel-Crafts acylations, and I told him, with isobutyryl chloride in benzene, you'll get an aromatic ketone from a Friedel-Crafts acylation. Mass spec should show 105. That would be the benzene ring and the CO fragment on a benzene ring, 105. 15, 29, 43, 57. Those are common alkyl groups. I want you to get the molecular ion, base peak, and fish out maybe 2 or 3 other peaks to help you with NMR and infrared. Thanks for watching, guys. Take care.